Everybody to another Motec webinar. My name is Pete Swinney and today's topic is boost control setup closed loop. As you can see, we have a similar layout to last time, and this subject today will cover a lot of the previous webinars that we've done on boost control. So the topics for today, as I said, we just want you to preview other boost control webinars, perhaps before doing this one. We'll go over the review of the plumbing, which is absolutely critical when it comes to a good boost control, is to have a good, it really starts with the mechanical side of the plumbing of the system itself. We will discuss some precautions. Again, it's important to go over these because the last thing we need you to do is damage the engine while you're getting this under control itself, getting it sorted. I'm going to talk about duty cycle because that word, or those two words, are referred to all the way through, and they really are the primary topic of explanation. Couple of methods. There's the open loop and closed loop. We'll talk briefly about that. Go through the menu items of the boost control system. There's lots of them, and while we're doing that, this time around we'll talk about the PID parameters, and I'll give you a brief explanation on what each of these means. We'll review the testing procedures. Not much different when it comes to closed loop. Same kind of procedure. Go through the aim table examples and the closed loop tables, some examples of how to fill those out with some real numbers, and finalise with some closed loop tuning. So if you are watching this webinar and you haven't viewed the other ones relative to boost control, I'd suggest you do that first. The webinars themselves can be found here on our website. There's actually a link on the front page, so if you go straight to our front page of our website and click on the icon right in the middle of the page there, you'll get to a whole host of webinars, and if you hunt through them all, you'll see one on helpful hints on boost control plumbing, our initial boost control setup, the open loop side, and Mark McCoy has also done one on PID parameters and a general explanation of how they apply to many of the Motec control systems. So just to review the plumbing, the types of systems on the plumbing, different ways you can plumb a boost control system. There are many, and Mandy's bounced out and in again. So basically, when we saw the first boost control systems, they were a simple spring-based system with a reservoir on top, and simply the boost from the compressor pushed against the spring. When the boost pressure reached the same pressure as the spring pressure, the wastegate opened, and there was no control at all of that. It was all determined by the spring. Next system, manual tap, bleeds air away from the line going to the wastegate actuator. As the air goes away, it means less reaches the actuator, therefore more boost here in the compressor before the wastegate opens. Simple system, works very well. Then we went to the electronic side, where we had a computer controlling a solenoid, and we could have the computer pulse the solenoid on and off to vary the amount of air being bled away from the system. If you wanted to move a lot of air away, you required a restrictor in the line so that you could get enough air out of the system to lift the boost high enough to reach the levels that you wanted. Then aftermarket systems started supplying three-way valves, and actually today is still not many on factory cars, but Motec supply or have available a three-way boost control valve, and that valve operates like this. So if you are using an integral wastegate such as the one we've been looking at, when the valve is open, then, or down here when the valve is on, just the same as a manual tap, the boost wastes away and the boost goes up. So the air gets bled out of the system and the boost lifts. When the valve is closed, then the pressure goes straight to the actuator and opens the wastegate at the same pressure as the spring. So the boost would go down. And then we're moving to remote wastegates, so a lot of high performance racing applications that use turbochargers without integral wastegates have remote wastegates. Now if you plumb these the way our drawing says to plumb them, when you buy a three-way valve, it actually works the opposite way for controlling the boost. Now what that means is when the valve is off, the boost goes up, which is the opposite way to the previous diagram. Where the valve is off, the boost goes down. So straight away, the difference between these two diagrams here is that the valve off in this case increases the boost, and the valve off in this case decreases the boost. So we need to know what plumbing you've got, what wastegate you've got. It will change how you set up your boost control system. Alright, so again, this is all covered in the previous webinars. So what is duty cycle? I will cover that again shortly. Just let someone else in. So duty cycle, this is a term that refers to the amount of on time of the solenoid, the boost control solenoid, versus the off time. So in the diagram here, we can see what the scope capture would look like of the auxiliary output trace on the computer that's controlling the boost solenoid. So normally we would power the boost solenoid with 12 volts, and the computer would ground it to turn it on. So when we see the signal going to ground, that is normally the normal way that it would be set up. And so if we are turning the signal on for 25% of the time and off for 75% of the time, then it's said to have a 25% duty cycle. And the cycle time, of course, is the time from each on time starting. Okay? So on time versus off time is the duty cycle as a percentage. Now, the thing that complicates that is sometimes we need the valve to be operated in the other way, depending on the type of wastegate system you've got, but I'll cover that again shortly. So when we connect up our boost control solenoid, we need to connect it to an auxiliary output and then configure that. So in the example in front of you here, we see it's connected to auxiliary output 4. The function is number 1, which you'll see when you go to connect it just by, or configure it just by pressing help. And then we get down to the parameters page. Now again, depending on the valve you've got, the frequency is normally very low, and 16 to 20 would cover just about all boost control valves. The polarity, which is what we're going to discuss now just quickly, is whether the solenoid is low for on or high for on. So depending on whether you need the solenoid to be on to lift the boost or the solenoid to be on to drop the boost, will depend on the number you put here. And the polarity, you change this from 0 to 1, as you can see on the help screen there. Now this page covers how that works. So it's normal to set the normal setup that you would normally understand is when the solenoid is on and the air is bleeding away, the boost would go up. And you can see here, this has the solenoid on as a 30% duty cycle, so it's on for 30 or low for 30% of the time and high for 70% of the time. Now sometimes it might be that turning the solenoid on actually decreases the boost, so we need to change the polarity. So by changing the polarity to 1, that actually reverses the signal in the auxiliary output setup. So this time it considers on as when the signal is high and off when the signal is low. You'll know you've got it wrong when you start putting numbers into your aim table, and when you put bigger numbers in, the boost goes down. So if that happens, then you need to switch the polarity around. So, precautions. We're setting this boost control system up, and depending on how big the turbocharger is and how small the engine is potentially, this will determine how much you could potentially overboost and hurt your engine. So we need to take some control of that. When you're setting up your manifold pressure sensor, it's in the place in the input setup. As you can see here, we're in the input setup of M800, and we are in the setup for the manifold absolute pressure sensor. You have the ability to put a default value in here. Now, it used to be, unfortunately, rather common that people would use incorrect sensors for the boost that they were running. Now, Motec sold commonly 3-bar map sensors, and a 3-bar map sensor, which is an absolute pressure sensor, measures 2 bar of boost and 1 bar of vacuum. So what that means is that it can only read up to 28 pound boost in the real world. Now, if you were running on the edge of that, maybe 30 pound boost, what would happen is that sensor would go into error because it's seeing more voltage than it's designed for. It's boosting past the level that the sensor is designed for, so the sensor would go into error. Now, when the sensor goes into error, the computer substitutes a default value. Now, this default value here, by default on our standard program, is set at 100 kPa. So what that would mean is if you left that at 100 kPa, overboosted the sensor, then at 30 pound boost, for instance, you would get the fueling for 100 kPa. Ouch. So big lean out and engine damaged potentially on the first outing. So we don't need that. So if you've got a 3-bar map sensor, then make sure your default value is 3 bar, so that it ever does exceed the sensor's capability and it goes into error, you can have it substitute that value. You can actually also control the diagnostic voltage here. So you can actually turn that off or make that 6 volts, 7 volts, so it never goes into error, but how you manage that's up to you. The other thing to do is you can turn on a high warning alarm and configure a number for you to be made aware when the boost is outside the area that you want. Now, if you're online to the ECU, that brings a big warning straight up in front of you and gets in your way for doing any tuning, so you can't miss it, and you have to acknowledge it to get rid of it. So in this case here, if the boost ever got to 270 kPa, a screen would come up in front of you and let you know. Now, if you're on a PWC, for instance, and you're out riding it, so you don't have your laptop connected, then this trigger can be added to the warning alarm list of warnings. And by ticking it on here, if you had a warning light configured and wired in, it would bring the light on, so you would know you've overboosted. So it's a good thing to configure and to let you know what's happening. The same thing for oil pressure, same thing for engine temperature, same thing for air temperature. All of those things can be configured to pop a screen up in front of you or turn on a warning light. Okay, and the other precaution that you can put in, which you need to use with caution, I'd suggest, is an overboost cut. So if it all goes horribly wrong, you can have the ECU cut all the fuel. In this example here, you can see where I've circled that we have a 250 kPa overboost cut. Now, this is very, very sudden. Basically, if the ECU sees this figure, the injectors are shut off, and if you're not hanging on, you're going to end up on the dash or over the front of the handlebars of your bike or PWC or whatever it is. So be aware that it's a very severe cut. So if we were looking at our previous example of 270 kPa being our warning, it would make more sense that our overboost cut was maybe 280 or 290. It's a sort of a holy Toledo. We need to stop this thing right now from getting any higher in the boost, otherwise we're going to damage it. So it's a last resort parameter, I'd suggest. So we have two methods of tuning boost with the ECU. The open loop method, whereby we put in the exact duty cycle that the solenoid will run at any given RPM or manifold pressure or throttle position. This is called open loop. The computer doesn't work on it becoming anything other than what you put in the table. So if you find that 60% duty cycle makes 1 bar of boost, then every time the computer sees 60 in the table, it will give you 60% duty cycle, and the engine should make around 1 bar. But if the turbo gets a little bit tired, maybe you go change altitude, you're in South Africa, you go up and down there, that will change the amount of actual boost that the engine would have or make, depending on the altitude, depending on the turbocharger. So what that might mean is that 60% duty in one area might make 1 bar of boost, but you might travel down to sea level and it might make more boost. So it's a reasonable way of controlling your boost, but if you don't keep an eye on it, it might not necessarily give you exactly the same result every time. So the true and correct way of maintaining a precise amount of boost is to do it in a closed loop manner. And what that means is that we have the computer doing constantly looking at the boost in the manifold and constantly looking at the boost control aim table of what you want, and then adjusting the duty cycle automatically on the boost control solenoid to try and achieve what you've asked for in the table. And to do that, it uses what's called PID algorithm. So these algorithms have to be tuned in order for the system to work correctly, because every system responds differently. A system with a large turbocharger, lots of plumbing, lots of a big intercooler, and lots of lag requires different PID settings compared to one where, let's say, it has no intercooler and the plumbing is all very short, so there's no delays. Large turbo versus small turbo, large engine versus small engine, everything affects how the turbocharger or how the boost responds for a given request by the computer. The computer works in microseconds, but the actual turbo system is very slow to respond by comparison. So there are two options, well, there are many, more than two, but the two common options that you would configure for the two that we've spoken about are represented by putting a number in the control channel on the first page of the setup. And so 0, as you can see on the help, refers to manifold pressure, so in other words closed loop, and 6, which is open loop, so no control system, just open loop, which is duty cycle control. Now if you've done or watched previous webinars and got to the point where you've done your tuning or your initial setup on open loop, you'll be ready to go from number 6 here to number 0, or to go to closed loop. But we'll just go through all the menu items again quickly, and so you have an understanding of what each one does. So the aim boost table, this is the critical table where the computer is looking to see what it is you want it to do. And in open loop mode, the numbers that you put in the aim boost table, here's the label for it here, the numbers here are duty cycle if you're in open loop. So here, my example, at 4,500 revs, I have a duty cycle of 54. Now when I tested that may have been, as I say, 1 bar of boost, but that's not going to make exactly 1 bar all the time. It's going to change with temperature, with ambient conditions, with turbocharger health, if you like, and you can't always exactly get the same result in open loop. This is an example of what the aim boost table would look like if you were configuring it as closed loop. It now has the actual manifold pressure that you want in here. What you need to understand though is that this is absolute manifold pressure. In other words, this is 80 kPa of boost, alright? So, you know, around 10 to 12 pound I think, if I'm correct. So here at 4,000 revs, we're asking for 200 kPa absolute pressure in the inlet manifold, and that represents 14.7 pound or 1 bar. Now, the normal position table, in open loop it's not used because in open loop we simply put our duty cycle numbers in the aim boost table. In closed loop, however, we use the normal position table to help the PID algorithm or give it a head start. It's called a feed forward. So if we know that at 3,000 revs and we want to achieve a boost of 200 kPa at 3,000 revs, and we know from our testing that most of the time 65% duty cycle is a good head start on that, then that's what we enter here. And when the computer goes to do the PID calculation, which it does around 50 times a second, it starts with 65 in this case. So it looks up this table and starts the calculation and says, right, 65% duty is what is normally a close enough number. And then it looks at everything else and looks at the existing error and then makes changes, but it starts on this normal position. This is really critical to getting a good closed loop system to work well. This goes for idle control, cam control, or every control system that you would have. If it's got it available, the normal position is the normal position table is the head start number, the feed forward number that the system will use. So it really is important to keep an eye on it and keep updating it with what the normal position would be. So another example, 4,000 revs, 180 kPa, duty cycle of 40. Okay. Overall trim, this is nice and easy. Don't use that that often. If for some reason you wanted to add or subtract an amount of boost in a hurry, maybe the riders come in or something, and you need to quickly add 10% boost, you can just fire into this table here or this parameter here and add 10%. You would only normally use that in a pressure situation. Normally, if you're going to make boost adjustments, then you would do them in the appropriate tables. Air temp compensation. So here you can see how we might use this. So here it is a plus or minus percentage of the main aim table. And anytime you're in any of these tables, you can just push F1 and it gives you an explanation of what the numbers would mean in relation to the system you're using. So here, if the air temperature went to 60 degrees Celsius, we're pulling out 20% boost, and at 80 degrees Celsius, 100% boost. But that doesn't mean it's down to no power. It just means it'll be sitting on the spring of the wastegate. So maybe you've got a 14-pound spring or a 10-pound spring in there. It'll still be making boost. So it's not the only thing you're going to need to do to protect the engine. Alright, same thing again, engine temp compensation. We've made sure that the rider, driver, whatever, can't overboost this thing or can't put too much load on this engine while it's still warming up. So basically it'll only run spring boost levels at 45 degrees, and that phases out completely by 50 degrees. And again, if it's getting above 98 degrees Celsius in the example, we're pulling out all of the extra boost at 100. We also have two generic compensations. This one here is full throttle timer, and we'll actually use this, potentially use this table like this to test our closed loop settings. So this has got a full throttle timer configured on it, and this is our generic compensation, a generic boost compensation, so we can put any channel up on this axis. And if you have a look here, when the customer nails the throttle, sets off the full throttle timer, the timer starts going along here, and we can see at 1.5 seconds we're asking the computer to pull out 10% of boost, and then at 2.5 seconds we're asking it to add 20%. So that's actually a 30% increase in boost, and then we're going to pull 20% out. So what we'll want to see is how that works in real life when he goes to test. This kind of stuff should actually be done on a dyno, where you could do this manually, but if you don't have the luxury of a dyno and you've got to test it in the real world, this is one of the ways you can do it. Second compensation, again, you can use it for anything. We can put this via in this case it's configured via a switch or a 9-position switch on the dash, and as the driver wishes to add and subtract boost for various reasons, this one was from a vehicle that runs a long distance off-road race, and often they will want a lot of boost initially, maybe to get past someone else, or a prologue style event where they've got to go quickly just for that amount of time. And then if they're out in front, they want to conserve the engine, they can just dial back the boost and take the load off the engine. And so this allows you to have a driver input on the amount of boost that's actually being applied. Right, proportional gain. In the open loop mode, you set this to 1 and leave it at that. And that simply allows the open loop system to work. In closed loop, we actually have to tune this, and this is one of the parameters that you need to play with to get the system right. So if you are setting this up for closed loop purposes, then start with a number around 0.3, maybe 0.2, maybe 0.4, but just let's make a start and call it 0.3 for now. This is a diagram of what the term proportional gain means. Now, gain in engineering terms means multiplier. So whenever you see the word gain, just think multiplies by, or a multiplier. And this is all of the proportional gain and derivative gain and integral gain is all about fixing the error, because the computer is trying to give you what you want. So for all these examples that I'm going to go through, we're going to assume an aim boost of 200 kPa. So that's 1 bar of boost. So in the example here, if we're just talking about the proportional gain element, currently in this example where the arrow is now, the engine's at 150 kPa. The ECU looks at what the actual manifold pressure is, the boost level. It looks at what it wants to be and calculates what the error between the two of them is. So in our example here, we have an error of 50 kPa. Now, the duty cycle at this point will be sitting, if we take a moment in time, at our normal position number. So if our normal position was 45, then the computer would start with a 45% duty cycle. And then it would look at what the error is. So the error between where the boost is now and where it wants to be is 50. So the calculation is the error, 50, times the gain factor. So our gain factor from our example is 0.3. So it's error times the gain factor equals the amount of duty cycle to change. So that's 50 times 0.3, which equals 15. So what that means is we start with 45, we're going to add 15% because we want the boost to go up, and we're adding 15%, which would mean 60. So in this case, the solenoid goes from 45 to 60, and the boost might go up. Now we've got an error of 20 kPa. So this time the computer calculates 20 times 0.3 equals 6. So the duty goes up by 6% to 66. And the next time the computer looks, we have an error of 10 kPa. So that's 10 times 0.3 is 3, and the duty goes to 69. Can you see by what's happening here that as the error decreases, the calculation decreases, and we get to a point where the calculation is so small that we can't get the boost to where we want because the error becomes smaller and smaller, and a 1% duty cycle change is not really enough to change the boost at all. So what I want you to understand that the proportional gain by itself won't get the boost to where we want it. And if we make the number small, we kind of get it like this, where it steps quietly to getting to what we want. Now, all of this might take half a second maybe. So it does it very quickly, but if we make this number too small, it still only just quietly gets on its way to fixing the error. So it won't respond quick enough is what I'm saying. But if you're thinking about what the proportional gain factor does, it works on making a change to the duty cycle of the solenoid proportional to the error. Big error, big change. Small error, small change. Integral gain. It's next in the menu, but when we're tuning, we don't actually do integral gain first. But I'll cover the topic now because it's next in the menu. We set it to 0 for open loop. That's easy. And for closed loop, we're actually going to start with it on 0 because of what the integral gain does. So the next screen will go through what part the integral gain plays in the overall calculation. So for now though, if we're actually talking about tuning a system though, we leave it at 0 until we're almost finished. So integral gain, this is about error over time. So if we pick up from where we left off on the last screen, so if we go back and have a look, at last screen the proportional had removed a good hunk of error and we're sitting at 194 kPa. What the integral does is it helps eliminate that final error, and the longer the error exists, the more it keeps adding. It's actually based on time. So we've got now from our last screen a duty cycle of 69% and a manifold pressure of 194 and an aim of 200. So we have an error of 6 kPa. So the calculation for integral is error times the gain factor. Now I need to discuss the gain factor. Let's, for the example, put in 0.2 here. So in our example, we've got 0.2 as an integral gain number. So it is the error times the gain factor, which is 0.2 per second equals the duty cycle change. So what that means is, if we go with the numbers, 6 times 0.2 equals 1.2. And what that means is 69% duty plus 1.2% per second change. So at that error, an error of 6 kPa, we would get the duty cycle adding by 1.2% per second. So if we held the boost at 194 kPa, the solenoid would just keep adding 1.2% per second. We'll just keep adding duty, adding duty, adding duty. Now, if we assume that it changes each time, the first step went from 69% to 70.2%. And we did get let's say, a minor boost change for that. Next time the integral calculates, looks at the error, 3 kPa. 3 times 0.2 equals 0.6% per second. So the solenoid keeps adding duty at 0.6% per second. Now, if the turbo is out of boost, like the turbo is at maximum speed and it won't make any more boost, so the turbo is going flat out, let's say, at 197 kPa. That's all it's got, and we keep the throttle nailed, and the system keeps trying to get to 200. The next thing it would just keep adding in this case 0.6%, adding 0.6%, adding 0.6%, and it would keep going and going and going until the duty on the solenoid was 100. And that is actually called integral wind-up. It means that if the system can't actually get to the aim, the integral will keep adding duty. So if this is a long straight on a race and the turbo can't make any more boost, but you're asking for it to make boost, the integral would keep winding the duty up, and as a result of that, you would end up with the duty cycle sitting at 100. And then next time we go to ask for a different level of boost, the duty cycle's got to come all the way back down, and that can cause a delay. So that's called integral wind-up, and we need to limit that from happening. And there'll be some parameters that we adjust down the line to help that. How are your brains going? All right. Next one, derivative gain, P, I, and D. This is the D. So open loop control, again, it's easy. You set it to 0. Closed loop, we have to start with a number. We're going to tell you to start with about 0.05. It's a very small number. Now, the derivative gain is like the brakes on the system. Again, if you've watched Mark's PID Parameters Explained webinar, it will give you a nice overview of kind of roughly what each term means using a different example other than boost control. It's good to get lots of different ways of understanding how it works. So, derivative gain. Okay, now, here we have a proportional gain example. Let's go back. Here's a proportional gain example with the setting being 0.3. Alright, so with the setting of 0.3, we had a boost change and it kind of worked its way up to getting to where we wanted it to be, but it wasn't in a hurry. Alright, so that as a means of controlling boost very quickly isn't satisfactory. So I'm going to give you another example here. Here's a proportional gain example with the number at 1.2, which in reality is what you would need to increase the number to if you're not getting adequate response. You might need to make it bigger. Now, this is maybe bigger than what you might end up using, but I'm just showing a larger number to help with the calculations, make it easier to understand. So we're back at our same error, 50 kPa. Now, in this case here, we're starting with the same duty cycle, 45%, and the calculation comes out at 50 times 1.2, which is 60. Alright, so 45 plus 60 calculates to 105, which would be 100% duty. So the solenoid goes to 100% duty, and bang, up comes the boost. Beautiful. This is the kind of response we want to see when we want boost. I mean, when the customer wants to get this thing to go, this engine to make power, we need the boost to come up. So here we have the boost coming up. But the reality of what happens is that it overboosts. It's too much. So we get a good response, but the thing goes way over boost. And then we have an error, 30 kPa in the negative direction. So let's look at what the computer would do in this case. 30 times 1.2, 36% change. Computer knows that it's too high and we need to pull that 36% off the solenoid. So we end up with a solenoid duty cycle of 64. Bang, down it comes. Oh, under, too low. And again, it's got to calculate a difference, and up comes the solenoid and over. And this is called hunting. So, without the use of derivative, which we haven't explained yet, but if we had no derivative gain in our PID, and you put a number big enough in the proportional gain to get good response, you would have hunting. And as you're tuning the system, hunting is what you will get until you get it correct. So we need something to back the solenoid off when we see that it's getting close. So in the real world, if you were controlling this manually and you could see the boost coming up, you would shut the thing off, because you could see at this point here, if you were looking at it, you could see that, hey, this thing is going to overboost if I don't do something about it. So the derivative gain part of the PID calculation does that. So here's an example of what the derivative gain does. It works on the rate of change of error. And this is hard to get your head around some of this stuff, but again, the help on each screen where the menu is, where each menu item where the derivative gain and PI proportional gain is, there's some help that explains it. So here's our scenario, and this is actually going to combine all three P, I, and D parameters together. So we've got an error of 50, and we put in, we're using our proportional example of 1.2. So we've got a proportional gain factor of 1.2. Our duty cycle starts at 45, and the numbers work. Error 50 times gain factor 1.2 equals 60. So same with the last screen, we get on with opening the solenoid and getting this boost up, and up it comes. So the derivative, which works on the rate of change, our example for the derivative is 0.15. The rate of change of error times the gain factor equals the negative duty cycle change. So the calculation is 150. Now I get that 150 from 150 RPM, sorry, 150 kPa per second. So if we look here, I've put some time lines here. So from, even though they're not that even, I'm sorry. So this is 1 second, 2 seconds, 3 seconds, etc. So this is a second in time at this example here. So I can see that we've approximately covered 50 kPa in a short amount of time, and that's calculated out at 150 kPa per second is what the computer has calculated that this line is heading up at. It calculates it very quickly, and it can see that the error is changing at 150 kPa per second. So it brings that into the calculation. 150 kPa times our gain factor 0.15 equals 22.5%. 22.5. So that means we take our duty cycle and take 22.5% off it. So that would make 77.5. So here is the effect that you actually get on the solenoid. Solenoid opens right up, the boost starts to change in a big hurry, the derivative factor calculates that it's changing in a big hurry and says, hang on chief, we need to pull the brakes on this. So it pulls out, in this case, 22.5% of duty cycle and helps to stop the thing overboosting. So that helps to curb the big overboost. So we get a big change to get the boost moving, and then as that keeps accelerating really quickly, the computer knows that it's accelerating quickly, is calculating the rate of change quickly, and backs off the duty, just like you'd close the tap or put the brakes on your car if you're approaching a stop sign too quickly. So if we've done a great job of configuring that and the boost ends up very close to what we want, the proportional no longer has much effect because the error between these two lines is very small. And what happens is the integral kicks in, and the integral over time sees the error and just starts winding a little bit of duty off. And it winds duty off until it gets to where we're going. And that's pretty much how it works. Now, if we're in a classroom, we could all discuss, you could all ask questions, but unfortunately that's not going to work for today. But if you keep watching it and trying to understand my way of explaining it, hopefully you'll get a bit of a handle on what it all means. So, that's PID. Now, to help with PID and how the system operates, we can actually clamp how much room we give it to move. So we can actually clamp the minimum and maximum duties that the system uses. So back here, where it maybe in my example used 100, the reality is it doesn't need to use anywhere near 100 to get to what it wants. So you can clamp it back using a minimum and maximum table. The way that you clamp it back will be different depending on your confidence of the system. So if you're struggling to get the PID right, or in the early days while you try and get the PID right, you will have a tightly clamped min and max duty area. So let me just jump ahead. Just looking for a screen here. Which doesn't seem to have made it in actually. Never mind. Let me carry on. What this table, basically this table, the minimum and maximum duty table, means is that at a given load and RPM, you can say to the system, never use, in this case the minimum duty cycle, never use any less than 35 at this point here % duty. Even if the PID calculates much less than 35, only ever use a minimum of 35. Now, it's not so important, obviously, that you worry about the minimums as much as you worry about the maximums, because it's the maximum duty cycles that will help you clamp it from over boosting. So in open loop, we want to just allow it to go to 100, because in open loop, the computer does whatever we say, as far as it just triggers the solenoid at whatever duty cycle we put in the aim table. But when we go to open loop, when we go to closed loop, when we allow the computer to make the decisions and potentially don't have our P, I, and D parameters right, you can have the computer calculating enormous numbers and the engine over boosting very easily. By clamping how much it calculates, we'll clamp the amount of the disaster, if you like. So what I'm suggesting is that if you have normal position numbers, let's say in this example, it's highlighted on a number of 69 at 3000 revs and 300 kPa. So if our normal position number, normally for 300 kPa at 3000 revs, we were running 60 as a number, then you run within 10 numbers of that while you get the system sorted, and maybe even less than that. Sometimes just for initial tuning you could run a maximum number of only 2 above what the actual normal position number would be until you get everything under control. Now obviously if you clamp it down too tight, then it will affect the system's ability to respond to big changes. It won't be able to open right up. So you are going to need to understand if it's responding badly and the system's calculating and wants to use, say, a number of 80, then you need to allow it to do that as you get on top of the control system better. Alright, positive integral clamp. This is going back to our integral wind up. Remember we spoke that if the computer can't get rid of an error, the integral will keep winding up further and further and further. So it can keep adding duty until the solenoid gets all the way up to, if you allow it, 100%. So what we can do is clamp how much it winds up. So in the positive direction, normally we're saying allow about 10% extra duty. If the computer hasn't got the fine amount of the error eliminated within 10% duty, then there's something wrong. Now that may even come back to 2 or 3% duty. The hard part is that some solenoids will make big changes for only 2 or 3, 4, 5% duty, say, and other solenoids, depending on their construction, might need 10% duty to make even a small change. So there's no real known numbers here. Everything is very much, you have to tune it based on how you see it. How is it responding? And understanding all these tables will help you to understand what numbers to put in to make it work properly. Negative integral clamp is simply the opposite of that. The amount of duty that the solenoid can take away to fix a minor error. So in this case, If it's sitting at 69% and the integral starts winding that down to try and fix a small overboost error, and it keeps going down, it clamps it down to 59% is as much as that will come down based on the integral part of the calculation. So testing, some checks you need to make sure before you go out testing and potentially damaging your engine. Always think the worst. Let's make sure we log the boost duty cycle channel. So if your boost control solenoid is wired into auxiliary 4, then let's make sure we log auxiliary 4. Let's make sure that the ignition numbers are lower and conservative in the areas where you would determine this is an overboost situation. So if you've got a number of 20, here in our example at 1 bar of boost, 7,000 revs, generally we need to see at least 2 degrees per 20 kPa out. So for every 20 kPa the boost comes up, at least 2 degrees should be coming out, if conservatively 3, and even more potentially. And if it gets to be really high boost, we really want to get that timing out of there so we don't have any chance of detonation. So, and safe fueling for the higher numbers as well. So in this example here you can see a fuel map, and this line here represents 200 kPa, the red line, and you can see by looking at how the fuel map is shaped that it actually has a kick up at the higher boost levels, where I've added some extra numbers just so we know that it's going to be nice and rich if it does boost up there. This whole tuning of the boost control system is not about tuning the lambda on the ignition. Everything should be safe. Get the boost under control. Get it so that whatever you type into the computer, that's what the boost you'll get. Then you can go and tune the fueling to perfection and the ignition to perfection. Alright, so your overboost cut, which we've covered, and your default manifold pressure settings we've covered as well. So the open loop testing, which you've got to do prior to your closed loop setting, is go into your aim boost table and type in different duty numbers to see what boost they make. So if you go in here and you put in a bigger number and the boost goes down, you need to go back to the polarity and change it around. Just so that everything makes sense and is easy to understand, we generally want number up in the aim table equals boost up. So you will find that once you've tuned the thing in open loop, you'll end up with numbers moving probably 30 to 40 from your lowest to your highest number. So your lowest number may be a 20, then the highest number is likely to be maybe 50 or 60. And in that sort of 30 or 40 number range, you should get the boost going up and down. No point in doing closed loop boost control until you can get that to work like that in open loop. If you're not making any boost at all, you've got something wrong. I had a nice example the other day. Guy watched my webinar, couldn't get the boost to work. He'd actually left a port on his wastegate uncovered. The wastegates have multiple ports to put your vacuum lines on. Didn't realise there was a plug missing out of it, and all the boost was getting away from the wastegate, and the system wasn't responding. So you've got to make sure the thing responds to the duty cycle commands. Maybe the turbo itself is no good. So sometimes if you are very, very careful, you can lock the wastegate closed, either by just pushing boost on the high side constantly, get rid of all the complicated plumbing and just make it real simple so that it never gets to waste boost away, and check and see how much boost the actual system will make. So manually lock the gate. You can even do it actually physically, mechanically, wire the wastegate closed, and very, very carefully see if it makes plenty of boost. If the engine and the turbocharger will make the boost mechanically, then you can get it under control. But if you find with the wastegate lock shut that the thing still only makes 8 pound of boost, then you're just wasting your time trying to get the computer to make more, because it ain't gonna happen. So Second part about testing, we just need to do small tests to start with because of the fear of overboost. On a dyno, we type in the numbers as it says there, and if you're testing on the road or on the water or something like that, type in a very low number to start with and get an idea of what's going on. Increase the number, the boost should go up. If it doesn't, go back to your setup. Alright, again, in open loop, find the duty cycle range that is going to be the range that is normal, because you're going to put all that stuff in the normal position table. Conduct the test for longer, so once you think you've got it under control and everything's working in open loop, like go do a race with it and get lots and lots of data on where the duty cycle needs to be for any given application. That is really good data. Anything running in open loop, you can record it, collate all that data and see what is the reality, what is the boost at full throttle, 5,000 revs. When we want 14 pound, what is the actual duty cycle at that time? Alright, so here's our two aim tables, open versus closed loop. Sorry, this is our open loop boost aim table examples left over from our other webinar. So we can actually change our boost numbers proportional to a number of different things. We can change them proportional to throttle position. We can change them proportional to a manually operated switch on the dash, or we could change them proportional to ground speed. The same is going to apply for closed loop. All these examples here show duty cycle numbers, so all open loop. And again, just going over previous webinar, here is what you would see in the data logging from a certain duty change. So here's auxiliary 4 duty cycle. The capture here shows it at 38% duty. You see the duty go up to around 60, and you see the boost lift from where it is now at 144 kPa up to, if we click there, around 200. So we're seeing a result of duty change, boost change, and this is what we need to have happen before we go to closed loop. Here's a second one where we configured the duty cycle to change based on a wide open throttle timer, so it just happened automatically. This could easily be from someone on the dyno changing the aim duty cycle in the table. So here the duty cycle was around 70 and we had a boost change, and then it went to 30 here and back up, then back down and back up, and we can see how the boost is responding to the changes in duty cycle. And it's at this point you can actually notice in reality just how slow the boost does change. So here the duty cycle went up to 70, and look, it's taken all this time here. We'd need to know exactly what that is on the time scale down the bottom, but maybe nearly a second for that to respond. Now that shows you how you've got to customize how quickly the system checks itself and calculates its different parameters for how the system responds. So if the system is a very quick responder, we need to use lots of lots of big high P numbers to respond quickly. If the system responds slowly, then the proportional gain numbers, the P numbers, need to be slow as well. We can't have it calculating too quickly, otherwise it just keeps calculating on a system that hasn't responded yet. Alright, so preparing for closed loop running. First thing we do, after we've got all that information and we understand what all the tables do, here we are an hour later, we need to fill out all our tables. So to fill out our normal position, we take all our information from what is the normal duty cycle for 4,500 revs. What's the normal duty cycle? So here is our aim boost duty cycle numbers that we used for open loop tuning, and we're transferring them down now to our normal position table. So all these numbers virtually, if they worked well there, you can transfer them into your normal position table. So if it was working at 4,000 revs, if we had the boost we wanted at 100% throttle, then let's put in a duty cycle of 76. So transfer it all down to here. Now it depends on what axis you've got. On the vertical axis here, you may have manifold pressure here, you could have ground speed here, you can have any number of things. But in other words, take your duty cycle numbers that you've learned to be correct and put them into the normal position table. Now fill out the aim boost table. So here we have our aim boost. So our aim boost is going to be proportional to throttle, and this helps the engine, give the engine feel. So when you start lifting your foot off the throttle, the boost starts coming down as well in this example. So our aim boost for 5,000 revs is 220 kPa, and through our testing we found that we needed, in this example anyway, a duty cycle of 88% to do that. So our PID calculation will start with 88% duty whenever it sees that we want 220 kPa at full throttle at 5,000 revs. Okay, so once that's done, we need to fill out our minimum and maximum tables. That drawing that I lost before is going to come up in a minute. Fill the tables out. So you have a minimum duty. This can be well underneath what you want, because initially while we're getting it set up, we don't care if it under boosts. And then we've got our maximum number. So our example before, I think, was 7,000 revs at full throttle. It was 88, so I've been really conservative here, and I'm just putting a number of 90 in, which is only 2 above. So fill all those tables out. So you'll end up with 3 tables that look like this: the minimum, the normal position, and the maximum. So the computer starts with this number here, 88% duty at 5,000, and no matter what the calculation, it will never go below 65 or above 90. Alright, so you are clamping how it works. Now, as I said last time, if you clamp it too tight, you're preventing its ability to respond. So you need to bear that in mind. But initially, this is all about getting this to happen safely. And here's the drawing I was looking for. So what you'll see in effect is the normal position duty changing, and the max and minimum duties just being either side of that, so that our PID calculation doesn't get wildly out of control while we get onto it. Alright, so after all this, it's a matter of, you've entered all the numbers, and it's basically go tune it. You go out there and test. It's the only way of finding out. Double check your precautions. Check your overboost cut. Can't say this often enough, as you've already worked out. Map sensor default and safe fuel and ignition numbers. Enter the recommended numbers into the PID tables. Small tests. Now, absolutely, whenever I'm doing this kind of work on anything with any sort of decent sized turbo, I'm just going to have a little look up there. Just going to open that throttle and feel the boost come on, and then whether it's on a dyno or look at it on the dyno, or download the logging and have a look. And you can see on that first little test if the boost is going to go crazy and way too much. And then just progressively start to test a little bit harder and longer. Just don't jump out there and go full throttle for 10 minutes or whatever and expect that it's all just going to work. I'm telling you, that's not the way for long engine life. So then, after you've got it safely under control and you can see that when you make a change, request a change, that you get a boost change, then start to do what we call a step test. Start to put the system under strain. So if it's on the dyno, ask for 200 kPa, and then while you're at full throttle, drop it to 150 kPa, and then ask for 250 kPa. So make the engine and computer respond to big step tests, and then you'll see how good your setup is. Now, let me just go back to some previous screens. Right, so if you ask for a big step change and the boost way overshoots the mark and then undershoots and does this hunting thing, then you've got too much proportional. go back through this webinar and try and understand what each part means. So if you ask for a big step change and it way overcooks it, absolutely over boosts it, then under boosts, then over boosts, it means your derivative is, your proportional is too high. You need to back it off. But if you make a change, a step request, and you go from say 200 to 240, and the thing, barely moves, it eventually gets to 240 kPa after 2 or 3 seconds, which is too long, then that means your proportional isn't enough. So what you're looking for is the minimum amount of proportional to get the response you want, to get the system to respond fast enough. And remembering, of course, that mechanically you can only make boost at a certain rate. So, don't be too critical. Don't be thinking that the boost is going to just respond instantly like a throttle response. There's always going to be a amount of time required for the boost to build and be measured by the map sensor. So as you use more proportional, you'll need the braking effect. So when the proportional responds nicely, you need to have some derivative in there to help it stop from overshooting. So this effect where the derivative pulls duty out as it starts responding quickly. So you leave the integral at 0 and stop that confusing things, and just work between the proportional and the derivative. So have everything low to start with, derivative very low numbers, all the numbers very low, and then just keep bumping up the proportional until you get the response good enough to be acceptable for a control environment. And then use the derivative to help it stop overshooting. And you have to work backwards and forwards like that. Now what you might find is that in reality you can't get it to respond perfectly, and certainly while you've got minimums and maximums clamped tight, it can never be perfect. But all of this will depend on how much time you've got to spend, how much time on the dyno, or time on the water, or time on the road that you've got to do the job. If you spend the time, you'll get a good result. Okay, let's go back to where we were. It's basically the last page. It really comes down to you now on how you conduct the testing. You conduct those step tests. You potentially can use a full throttle timer to conduct step tests for you if you can only do it out on the water, or if it's a single-seater race car and you haven't got a dyno and you've simply got to send someone out, then you can use a full throttle timer to increase and decrease aim duties and see how it responds. Check the response, and again you can adjust the P to get the minimum adequate response, adjust the D to stop the hunting, and adjust the I after the two are set. So the integral is only to eliminate that last little error. Alright, and also keep an eye on the appropriate min and max duty cycle numbers. PID tuning is extremely difficult. Don't be disheartened if it doesn't all come together quickly. If you're absolutely adamant that you want to get this perfect, and there's no reason why you can't expect to get it there, if you've got a very high-end system and you want to get it perfect, then it's useful to learn about PID using a different type of control system, such as idle control or throttle control, even cam control. So learning about PID using a less stressful parameter, let's say, is a good idea. People go to university for years to learn about PID, and it's not an easy thing to understand and to tune, that's for sure. Nils has just asked a question which we might just cover quickly before we finish off, about why we would use the throttle position on the y-axis. And here on the aim, here we've got boost aim table. So throttle position is a way of allowing a customer to get feel on the throttle, to allow the engine to feel more like a naturally aspirated engine. So I'll give you an example, and I'll use current PWC Yamaha as an example. A Yamaha PWC, the SHO platform, 1800cc, supercharged, makes maximum boost, even supercharged. This is still relevant to this conversation. At full throttle, it might make 200 kPa. At 60% throttle, it still makes 195 kPa. And it's not until you get down under 60% before the boost will drop away. So what that means on a racetrack is that if the racer, driver, rider, whatever, comes up to a corner, lifts his finger off the throttle by 20%, it doesn't slow down. So when that comes to a turbocharged application, it's even more prevalent. So what happens is, if in fact I got a log file today from a customer, said his engine wasn't going as good as what he expected, and it had almost full boost, and he was at 30% throttle. The drive-by-wire motor had another compensation issue, and the drive-by-wire motor was locked at 30%, and it was still making nearly full boost at that. So a way of giving that feel back to the throttle is to make the boost proportional to the throttle. So when the customer starts pulling the throttle off, the boost starts coming back. Does that answer your question, Nils? Hopefully. Just using the M800 for its ability to be fully configurable, you can put any axis here you want. So it's used for many, many different types of racing, from commercial applications to closed course racing. And Nils isn't happy with my answer yet, but I'll have to talk to him offline about that maybe. Alright, so that's effectively it. Thanks for your attention for this very long webinar. Hopefully we've covered most of it. The previous webinars, as we mentioned at the beginning, are on our website on the front page, or at the link here. And you can ask questions on our forum, more detailed questions if you like, on our forum. And you'll see on there a lot of questions about boost control now. Alright, thanks for attending, and we'll catch you next time.